Alright, this is 1.5, part 2 of chapter 1. It's dealing with stoichiometry because we're still dealing with moles. In this case, we're dealing with empirical formula and molecular formula. So empirical is the smallest whole number ratio of the element. So it's the reduced amount. Like the Death Star got reduced. Just kidding. And then molecular formula is the actual real number of atoms of each element present in that molecule. Molecular can be empirical sometimes if it's already the correct molecular formula and it cannot be reduced. But the empirical formula is the reduced amount. So here's some examples. Empirical formula on the left-hand side. Water, H2O, cannot be reduced. HO, hydroxide, cannot be reduced. SO2 cannot be reduced because it's 1 and 2, and then C2H5 cannot be reduced because 5 is an odd number and 2 is even, so they can't be reduced. Molecular, water is a molecular formula. It is an actual compound, H2O. Hydrogen peroxide, H2O2, is an actual compound, and it can be reduced since they're both 2s. It can be reduced to HO. SO2 is a molecular compound. It's a hazardous gas that causes acid rain, but it cannot be reduced, but it is a molecule. C4H10, which is butane, is an actual molecule and can be reduced, can be reduced to C2H5. So, question checkup number 8. Write the empirical formula for each compound. Hydrazine is a very explosive compound, can be reduced. Octane can be reduced to C4H9. Benzene, CH, and then ammonia cannot be reduced, so the molecular is NH3. Alright, to determine the empirical formula, first step is you gotta find the moles of each element, not the mass. You'd be given mass or percent, and you have to use the molar mass to convert to moles. Step 2 is to find the ratios between each element. So you always do the ratio of large over small, and that will give you a ratio. Here, example. A compound is made up of sulfur and oxygen. 25 grams of each of sulfur and oxygen are present. Find the empirical formula. So you start with your given, which is 25 grams. In this case, we'll start with sulfur. Divide by the molar mass of sulfur, which is 32. And I get 0.780 moles of sulfur. Same thing with oxygen. You have 25 grams of O, not O2. This is elemental. And divide by 16 or so, and you get 1.56. So those are the moles of each. So that's step 1. Step 2 is to find the ratio, large over small. So you're going to do oxygen over sulfur. 1.56 divided by 0.78, and you get a 2-to-1 ratio. So what's that mean? That means for every 1 sulfur, there's 2 oxygens. So the formula would be SO2. Alright, here is the workout example on page 9, number 7. We have magnesium burned with XX oxygen to make magnesium oxide. We have 0.486 grams of magnesium, and it makes 0.806 grams of magnesium oxide. Question is, we'll calculate the empirical formula for magnesium oxide. Okay. We want to know the simplest ratio in which magnesium and oxygen react according to the given data. If this seems familiar, you guys did this experiment in pre-AICE when you burn magnesium in a crucible with oxygen. So ultimately, we got to define the mole ratio between Mg and oxygen. So we have to find what should we do first with the moles is to get the moles of Mg and O2. So you need first find the mass of oxygen. So we have the mass of magnesium, we have magnesium oxide, so the difference is going to be oxygen. Now we know the masses Mg and O. Next up is find the mole ratio, so how they react. So we have to convert to grams to moles using the molar mass. So we took the grams of magnesium and divide by the molar mass of magnesium. They cancel out, and I get 0.02 moles of Mg. Same thing with oxygen. we have 32.32 divided by about 16 grams. And again, I get the answer of 0.0200. So they're the same value, so the ratio has to be 1 to 1. So that means the formula is going to be MgO. Alright, an unknown, example number 2, an unknown compound contains both sulfur and oxygen. 40% sulfur, 60% oxygen. Determine the empirical. Uh-oh, math alert. Attention, attention. We treat percentages just like grams. It doesn't matter how much sample you have, therefore the percent, make it grams. So that's easy. Convert any percent you have for empirical formula and just change it to grams. Therefore, instead of 40%, it's going to be 40 grams. Instead of 60%, it's 60 grams. So we have 40 grams of sulfur divided by the molar mass of sulfur, and I get 1.25. Yeah, 60 grams of oxygen divided by 15.999, and I get 3.75. So there's more oxygen per mole than sulfur. That's why you have to get to moles, because mass is relative to its element. Large over small, and you get a ratio of 3 to 1. So the formula is SO3. For every 1 sulfur, there's 3 oxygens. Homework problem, here you go. 90% carbon, 10% hydrogen. Deduce or find the empirical formula for this hydrocarbon. Alright, how do you find molecular formula from the empirical? Again, it's stoichiometry, but it's ratios again. So for every single empirical, it either gets doubled or tripled or quadrupled or 5 times, whatever druple it is, that amount. So think of this example of Ritz crackers and cheese. I have 4 sandwiches of Ritz crackers and cheese. That means I need 8 crackers and 4 pieces of cheese. That can be reduced in empirical formula to 2 and 1, 2 crackers and 1 cheese. So let's say, for example, a cracker weighs 2 grams per mole and a cheese weighs 1 gram per mole. The molar mass, this needs to stop, for the molecular is 20 grams, because there's 8 crackers. 8 times 2 is 16, and there's 4 cheeses, it's plus 4. And the empirical molar mass would just be 3. I'm sorry, 5. Sorry, there's 2 crackers, 2 and 2, and then 1 cheese. Oops, let me go back. Sorry. That means there's 4 times, the molecular molar mass is 4 times as the empirical, so that means you multiply the empirical 4 times as much. That's why you get Cr8 and CH4. So, how do you find molecular? First step is to find the empirical, just like the molar mass using the periodic table, just like any other molar mass. 2, you find the ratio between the given molecular mass, so you have to be given the molecular mass, and the empirical, large over small, so it's always going to be molecular over empirical. And whatever ratio that is, you're going to multiply it, the empirical, by that. So we made up a compound, previous problem, of SO2. The molar mass of that compound is 128. We found the empirical to be SO2. So to determine the molecular formula. So the first step is to find the molar mass of the empirical, so SO2, which is 64.06 grams. So how much do we have to multiply that number to get to 128? Mental math should say twice. So it's a 2 to 1 ratio, so that means the empirical got reduced by half. So that means the molecular is double of that in the empirical. So that means the molecular formula would be S2O4. So you can see that it gets reduced to SO2. You can double check your work. You can find the molar mass of the molecular formula. It should come out to be 128.12 grams per mole. Alright, another example. This is a little more involved. We have the molar mass of your molecule, 26 grams. It contains 1.85 grams of hydrogen and 22.15 grams of carbon. Determine the empirical and molecular formulas. So we have to find the empirical first from the given information, hydrogen and carbon. So you have to convert, you can't just use grams, you gotta convert to moles first. Always go through mole land, moleville, mole town, whatever you want to call it. So we have 1.85 grams of hydrogen, divided by the molar mass of hydrogen, which is 1, and you get roughly 1.84 moles of hydrogen. Same thing with carbon, we have 22.15 grams, divided by the molar mass of carbon, which is 12, and you get 1.84. Wow, that's the same value. So the ratio is a 1-to-1 ratio, so the empirical formula is CH. So basically our goal is how many CHs are there to get the molar mass of 26. The molar mass of CH is 13. So mental math should be able to figure out that's twice as much. So the 26 divided by 13 is 2. So the molecular formula should be C2H2. So here's a quick review again. Find the molar mass of your empirical from the periodic table. Find the ratio between the molecular and the empirical, large over small, so always molecular over empirical. Sometimes the molecular is the same as the empirical.